Hi and Assalamualaikum. I am Muhammad Imran and I am a final year student at School of Mechanical Engineering Uitm. As you know, I just finished my proposal and research for final year project 1. Based on my findings, there are a few reasons why I choose this topic. First, CFD analysis have a great potential to save time in the design process. It is also cheaper and faster compared to conventional testing for data acquisition. CFD analysis cannot fully exclude physical testing, but all design quantities can be measured at once. I will use this finding to calculate coefficient of drag and coefficient of lift. Without further ado, let's move on to the recorded presentation. I will be presenting on computational fluid dynamic analysis for my final year project 1 presentation. As for the project summary, it is to measure the fluid dynamics of a hydrogen car to improve its performance during races. It will also be greatly beneficial towards the Uitm Shell Ecoplanet team towards the upcoming race against other countries. The aim of this research is to identify alternative simulation techniques that can solve industrial application while still offering solution with appropriate accuracy and resolution. For the introduction and background, CFD analysis is used to determine the forces used and the vehicle's performance during movement. CFD is also used to analyze the efficiency and ability of the vehicle performance in comparison with other vehicles. The goal is to accurately measure the drag and lift coefficients by stimulating the airflow around the vehicle. For the literature review, the history of vehicle aerodynamics is divided into 4 periods, which is basic shapes from 1900 to 1925, and then streamlined cars from 1921 until 1955, and then moving on to detail optimization since 1974, and then shape optimization since 1983 until now. Basic designs were borrowed from ships and aircraft for the first attempts to construct vehicles with a superior aerodynamic shape. These are the methods for CFD. It is divided into 2 parts, which is conventional methods and also accelerated methods, and it is divided again by advanced numerical methods and hardware techniques. These are the example of the literature review that I found, which is aerodynamic study of Formula SAE car, and then CFD analysis of pace Formula 1 car, CFD study of section characteristic of Formula Mazda race car from 2004, CFD analysis of concept car to improve aerodynamics in 2011, and also a following car influences cyclist drag in 2015. The objective of this research is to determine the coefficient of drag CD and coefficient of lift of Uitm Shell hydrogen car. It is also to determine critical parameters that have significant effect on the CD and CI of Uitm Shell hydrogen car, to optimize the coefficient of drag and coefficient of lift, and simulate the process using ANSYS and SolidWorks software. The scope and limitation of the project. First, numerical simulation will not be as accurate as real-world experiments. Due to the COVID-19 restrictions, we were not able to enter Uitm to make a real-world analysis regarding the CFD of a Shell hydrogen car in the lab. This experiment will be conducted on ANSYS and SolidWorks software to determine all the variables value for CD and CI of the hydrogen car model using fluent and CFX fluid dynamics. Instead, we are limited on conducting a simulation at home with guidance from supervisors only. As for the methodology, first is designing. The model will be designed in SolidWorks according to Uitm Shell hydrogen car. Then we need to transport the file. After the design was completed, the file will be transferred into ANSYS software to start the CFD analysis. Then we need to formulate the flow problem. The first stage in the analytic method is to formulate the flow problem. Then model the geometry and flow domain. The body in which the flow will be investigated must be modeled. In most cases, this entails modeling the geometry with a CAD software tool. Then we move on to establish the boundary and initial conditions. The simulation begins with an initial solution and progresses through an iterative process to a final flow field solution. Then we will need to create the grid. The flow domain is discretized into a grid. Grid generation entails first defining the structure and topology, and then producing a grid based on that topology. Then we need to establish the simulation strategy. The simulation strategy includes deciding whether to use space matching or time matching, which turbulence or chemistry model to employ. Then we need to establish the input parameters and files. The CFD code often necessitates the creation of an input data file that contains the values of the input parameters associated with the intended strategy. Then we need to perform the simulation. The simulation is carried out in a variety of ways, including interactive, batch, and distributed processing. Then we move on to monitor the simulation for competition. As the simulation progresses, the solution is observed to see if a converged solution, which is iterative convergence, has been obtained. Then we need to run the simulation again. The process of obtaining the desired flow attributes from the computed flow field is known as post-processing. Then we will start on make comparisons. The calculated flow properties are then compared to the results of analytic, computational, and experimental research to determine the validity of the computed results. Then we will need to repeat the procedure to check for sensitivities. The sensitivity of the computed result should be investigated in order to comprehend probable discrepancies in the accuracy of results or calculation performance. And lastly is document. Documenting an analysis finding entails detailing each of the steps in the process. Then we move on to preliminary results. CFD methodology setting use consists of three essential steps, which is computational domain, also known as pre-processing, aerodynamic computation, also referred to as solving, and also numerical result, also referred to as post-processing. And this is the example that I obtained from ANSYS software on my meshing processes. Meshing is the process in which the continuous geometric space of an object is broken down into thousands or more of shapes to properly define the physical shape of the object. The more detailed a mesh is, the more accurate the 3D CAD model will be, allowing for high fidelity simulations. One of the purposes of meshing is to make the problem solvable using finite element. By meshing, you break up the domain into pieces, each piece representing an element. Then, this is the velocity magnitude that I obtained. I also managed to create a graph for the velocity. The magnitude of velocity means that the vector is the instantaneous speed of the object. A velocity vector represents the rate of change of the position of an object. The direction of the velocity vector is directed in the same direction that the object moves. The magnitude of a velocity vector gives the speed of an object, while the vector direction gives its direction. And these are the drag force magnitude that I obtained from ANSYS. Drag coefficient in fluid dynamics. Drag is a force acting opposite to the relative motion of any object moving with respect to a surrounding field. The magnitude of the drag force, Fd, or coefficient of drag, Cd, is found to be proportional to the square of the speed of the object. As for my discussion and conclusion, I was able to simulate complicated processes online. Various methods developed different approaches capable of shortening the simulation time till it reached or exceeded the real process time in some circumstances. Next, the simulation findings were found to be quite close to the officially supplied numbers, and all the objectives was able to achieve. Thank you, and that is all from me.